So, we had, let's say we got a simple closed curve here, parameterized by an r of t. And if we write that sort of parametrically there, we got our x of t and y of t. And then we could get the work or the circulation, depending on what we're looking at there, would be the integral around that curve. F of t dot r prime of t dt. And r prime of t, remember, take the derivative component wise. Okay, and so that's kind of what we were looking at yesterday. So then at the end of yesterday, we talked about the concept of flux. So instead of adding up things as you go along the curve and seeing how much of the force or flow is in the direction of the motion, flux is looking at how much is going across. So if your field's, if your field's doing this, and we try to figure out how much is actually going across, then instead of dotting it with a tangent vector, we have to dot it with a normal vector. So we talked about, if you've got your, if this is your x prime, y prime here, that's your r prime. Then if we wanted a normal vector, we had two options. We switch the components and make one of them negative. So you have like a y prime minus x prime, or a minus y prime x prime. And so depending on the orientation of your curve, like if you're traversing the curve counterclockwise, which is typically the default for reasons we'll talk about next week, then you can select which one of these normal vectors you're after, whether you want the flux out of the region or the flux into the region. And you can go through and make your argument here. If in this particular case, x prime and y prime are both positive, so if you want the the outward flux here at 90 degrees, the x component would be positive, the y component would be negative. And so that leads us to our selection here for outward flux. So if you have counterclockwise rotation, outward flux would be given by this formula. You got y comma minus x. Right? So that's, I think, where we left off last time. And then example 7 is we're going to work through this example. So if you look at your the new take-home, you've got a problem like this. So we're going to work through this. You've got this field, f of xy equals 2y xy. C is the triangle with these vertices oriented counterclockwise. Right, so this is very similar to the one you've got to work on for next week. So we've got 0, 0, 4, 0, and 0, 2. And so here we go, this way, this way, this way. All right, so that's our curve C. And we've got this field here. And so we have 3 line segments we're working with now. Flux, just like work, is going to be an additive thing. If we're trying to figure out the outward flux of this field across the curve C, the outward flux here from this region here, trying to add up how much stuff is sort of getting out from here. That's it's flux. I could figure out how much stuff is getting out across the bottom side, this side here, and this side here. So we're going to label the sides. We'll call this side 1, side 2, side 3. And so we'll have 3 little flux integrals and set all these up, and then we'll look at what's going on geometrically to see if our answers make sense. So if I look at side 1, side 1 is a line segment that goes from 0, 0 to 4, 0. And so I could parameterize that. R of t equals x starts at 0 and goes to 4. So 4t, and the y always stays at what? 0. So that's my parameterization of that line segment. So my r prime of t, well, we don't do that yet. So that would be x of t would be 4t, y of t would be 0. All right, so that's step 1, is we found that parameterization. Step 2, we're now going to get the field, which is given to us in terms of x and y in terms of t. So we go back, f is 2y comma xy. So f of t, you plug in the x is 4t, the y is 0. What's going to happen to this field? Yeah, it's just going to zero out. All right, so there's nothing going on. When y is 0 on the x-axis, there's nothing going on. So now step 3 would be to take your f of t dot, and then instead of r prime, since we're doing flux here, it's y prime comma minus x prime. But my field here is 0, 0. So it really doesn't matter what I got going on here. I mean, this would also be 0. That's going to be 0. And so step 4, what's the flux going to be? Yeah, we're integrating 0 to 1, 0 dt, we get 0. So that means that there's nothing getting across that line segment. Yep, so that's it. And that's because the field is 0 there. So nothing's moving at all. And once again, we'll see that geometrically when we get through that. Okay, so that was, I should say that was side 1. So now we'll go side 2. Side 2, we start at 4, 0 and go to 0, 2. And we're going, once again, we're traveling things counterclockwise, so we're going that way. So to get our parameterization, we're starting at 4, ending at 0. So the x value we start at is 4, and we're going from 4 to 0, so that's minus 4t. Y starts at 0, ends at 2, so that's 2t. T from 0 to 1, traces that out. So that gives us that our x of t is 4 minus 4t. Our y of t is 2t. And now we got to get our field, f of xy, which is 2y xy. We need that as a function of t. So once again, we plug in what the x is and what the y is. So 2y would be 2 times 2t. Xy would be 4 minus 4t times 2t. And so f of t would be, I get 4t in the first component there. What do you get when we multiply out that second component? Yep, 8t minus 8t squared. There you go. All right, now since we're doing flux, we need to calculate f of t dot y prime of t comma minus x prime of t. So this is the difference between work, circulation, or flux. And flux, we're multiplying by this, we're dotting it with the normal vector because we're seeing how much of the field is getting across the segment here. So we got a 4t, 8t minus 8t squared. And now I need y prime comma minus x prime. So go back here. Y prime would be 2. Minus x prime would be minus a minus 4. Everybody okay getting that normal vector there? So now we get back to dot product, multiply corresponding components, add the results. So I got the 2 times 4t plus positive 4 times 8t minus 8t squared. I get an 8t out of that. I get a 32t minus 32t squared. So when it's all said and done, I get minus 32t squared. And then how many t's do I get? Plus 40t. So at any given time t, as I'm moving along that line segment, this is giving me how much of the force is in the normal direction. So then to get the flux, I'm going to integrate from 0 to 1. This dot product. So that'll add it all up. Minus 32t squared plus 40t dt. So I get negative 32 thirds t cubed plus 20t squared from t equals 0 to t equal 1. So negative 32 thirds plus 20. If I wanted to write this as thirds, that'd be 60 thirds minus 32 thirds, which would be how many thirds? Yeah, 28 thirds. Now once again, since we have a positive flux and we're looking at outward flux, all right, so we're on this thing here. We got this field going. We're looking for outward flux. So we're looking for the field, right? We're looking at this direction as we go across. Since the outward flux is positive, that means when I put my field in here, and when we look at the field should be pointing more outward than inward. You follow? There should be a definite, we should be able to see flow going outward across in that direction since it's positive. All right, now we got to go to side 3. Side 3, we're going from 0, 2 down to 0, 0. So we're coming down that way. So my R of t here, we're starting at x equals 0, ending at x equals 0. So x is always 0. I'm starting at y equals 2. I'm ending at y equals 0. So there's my 2 minus 2t. So that gives me that x of t is 0. Y of t is 2 minus 2t. And now I go into my vector field, f of xy. Same field we've had for the last two parts. It's 2y comma xy. But we need to see what this looks like in terms of t. So to get f of t, everywhere I see a y, I'm going to plug in the 2 minus 2t. Everywhere I see an x, I'd plug in a 0. So this simplifies to 2 minus 2t, 0. Oh, thank you. Yeah. I think I saw the 2's there. And there we go. Thank you. 4 minus 2t. So if I look at what this is saying, 4t, thank you. What this is saying here is that if I look at this field, if you look at this field, notice that the y component of this field is always 0. That means this field only has movement in the x direction. So as I go down here, like when t is 0, I'm at the top here. The field is positive 4. So it's looking like this. And then as it comes down, when t equals 1, it's 0 down here. Because we know the field is 0 all the way along here. So we knew that happens. But if you look at what's happening, this field is always pointing to the right, but it's always pointing this way. So let's look at the outward normal then. The outward normal would be pointing that way. So we'll see what happens here. So now I need to calculate the integrand f of t dot y prime of t comma minus x prime of t. So here's my 4 minus 4t. Zero dotted with y prime of t. So the y prime of t would be negative 2. And then x prime of t, since x is 0, that's going to be 0. And so here we go. Calculate this. Multiply the corresponding components. Add up the answers. We get 4 minus 4t times a negative 2 plus 0 times 0. And I'm going to get minus 8 plus 8t. And then to calculate the flux, going from 0 to 1, minus 8 plus 8t minus 8t plus t squared over 4 from t equals 0 to t equals 1. So here I get a grand total of what? I get a negative 8, excuse me, not t squared over 4, 4t squared. There we go. So what do I get? What's my grand total for flux that way? Negative 4. Okay. Now, if the outward flux is negative 4, that must mean that the flow must be coming, the net flow, there must be more coming in across that side than going out. And you can see that right here. When we got to this, we could actually see that. The field is pushing stuff this way, which is opposite of what's going out there. So that makes sense there. All right, so now to answer the question here, the total flux, you just add the flux across each side. So the flux out the bottom was 0. The flux along the diagonal was what, 28/3? The flux along the other side, the left-hand side was what, negative 4. So you go through and get your common denominators, and what do you end up getting for the total flux? 16/3. So that's a positive number, which means even though you've got stuff coming in one edge, there's more going out across that diagonal than coming in. So and then we're going to fire up the vector field plotter here in a minute. But we've got 0 flux here, we've got plus 28/3 here, and we got negative 4 here. And this is outward flux again. So -4 here means that the net is there's more coming in than going out. Nothing's happening here. Here we've got more going out than coming in. Since we have more going out here than is coming in here, the net effect is there's more going out of this region than coming into it. Does that make sense or not? Do you see what's happening there? Well, for flux is anytime you have stuff getting across. So like if you think about this like as a cell, you've got osmosis, moving things across membranes, the concentration on one side versus the concentration on the other side. That's a biological example. But if you're trying to look like magnetic flux, an electromagnetic flux, how much of a field is getting across? In fact, if you go to the gas station and you're pumping gas, if you look on the hose, it'll have a rating of flux because they're looking at how much vapor is getting across the tube there. So flux is a big deal. Now in 2 dimensions, like I said, you can think of it like in 2 dimensions. I think in 2 dimensions I think of just like a cell. Like you've got this cell membrane here, how much is getting across. But we're going to revisit flux here in a couple weeks in 3 dimensions where we're looking at the flux across a surface in space. Yeah, gravitational flux. Yeah, it's the dual notion to work, because work and circulation are in the direction, so it's a dot product with a tangent vector. Flux is a normal direction, so it's a dot product with the normal vector. So it's this duality of parallel and perpendicular, which we actually set up all that machinery back in at the beginning of the course. So like I said, I love Calc 3. I think of all the calculus classes, of all the classes I teach, period, Calc 3 is the one where it's like everything got set up in the first 12 weeks, and now we're putting it all together. There's not a lot of new stuff. There's just new ways to put the old stuff together. So yeah, good question though. So let's look at this once again. Oh, I did want to point out I did upload the parametric tricks of the trade. This was a handout from chapter 13. It's up here again. So if you need to pop this down and print it out, this gives you basically the recipe sheet for how to build parameterizations. So line segments, circles, things like that. So I did remember to put that up there. Let's take a look at the vector field. So here's the vector field we're working with, 2y comma xy. And we can actually just draw in the triangle we were working on, right? We were going from 0, 0 to 4, 0 to 0, 2. So we could draw this in. There it is. So here's where we were going. And you can kind of see here, you wanted to kind of, we can like increase these so we can see a little better what's going on. But you can see here on the x-axis, there's nothing happening at all. The field is 0 along the x-axis. So that's why we don't get any flux. If we were looking at work or circulation, we wouldn't get any of that either. It's just totally zeroed out. And then you can see as we come across here, you see how the arrows are pointing this way? So the arrows are pointing as if we've got a flow coming out. And then on this direction, you can see we got the arrows coming in. So if I kind of look at sort of the what's called the streamlines, I guess, of this, we'll talk about those later too. You can see that we've got stuff coming in through this side and stuff leaving on this side. But there's more stuff getting across and leaving here than there is coming in over here, which is why the net outward flux is positive. So there's a problem on your the second problem on your take home is one of these flux integrals that's across a triangle, very similar to what we did here. And I have you graph this. You can plot it, print it out, sketch a triangle or whatever. to try to explain some of the answers you get, because there's some other interesting things that happen there. All right, differential forms of line integrals. So suppose you write the vector field in component form. So if you've got f of xy, the x component, we'll call that function m. So we have m of xy, comma n of xy. That should be a comma. I can't tell if it's a comma or not. Then if you go through and work this out, f dot r prime, you'd have m comma n dot x prime comma y prime, and then you do your dot product. So you multiply the corresponding components and you add them up. You would get down to this expression, and then using the properties of definition of differentials, I should say, x prime dt is dx, and so this would be the differential form of a work integral. And as has been the custom in this course, if you did have a three-dimensional field, then you just literally tack on the z component. Okay. So that's work and circulation. So this would be work and circulation. It would look like that. So let's take a look at this integral. This is how they present the integral to us. We're looking at the integral over c, x dy minus y dx. C is the portion of parabola y equal x squared, x between 0 and 2. And once again, the goal here in section 17.2 is we want to get this in terms of just one variable. And so we have all the same sort of mindset we had earlier. In this particular case, they're telling us y as a function of x straight up. So if y equals x squared, I can calculate the differential. What's dy? Yeah, 2x dx. And so my integral here, I'm integrating over the curve c. The curve c is determined by x 0 to 2. I've got x times dx, or excuse me, dy, 2x dx, minus y, which is x squared dx. So I'm just integrating 2x squared minus x squared dx. And I think we can sneak that in there. That would be what, 8/3? So if you see an integral that looks like this, it's a line integral. You can interpret this line integral as a work integral, or actually as a flux integral. We'll talk about that here in a minute. Any questions on how we plug the stuff in to get one letter? That's pretty much what you got to do. All right. Find this integral where c is the helix r of t, 3 cosine t, 2 sine t, 4t. T goes from 0 to pi. So we've got what? 3z dx minus 2x dy plus y dz. And the curve C is this helix. 3 cosine t, 2 sine t, 4t. So it's elliptical helix. And t runs from 0 to pi. So once again, we have a line integral. They give us the parameterization. So what we need to do is to rewrite this integral in terms of what letter? So what's going to be the, yeah, t, that's the independent variable. So I go from this parameterization, I can identify my x, y, and z. On this helix, x is always going to be given by 3 cosine of t. Y is going to be given by 2 sine of t. Z is going to be given by 4t. And from here I can calculate my differentials. Yep. So my derivative of x with respect to t is minus 3 sine of t, and to get the differential you tack on the dt. Derivative of y with respect to t, that's your 2 cosine of t, slap on the dt, and then finally that would be 4 dt. So we're going to put this as an integral of t. The curve is traced out as t runs from 0 to pi, so that's going to be our integral from 0 to pi. We've got 3z, which is 4t, dx minus 3 sine of t dt. So this is my 3z dx minus 2x dy this is my minus 2x dy plus y dz so this is my y dz. Do you see how we got all the t stuff plugged in? And now you go off and integrate that. So what would you do for this first part here? You'd have like a negative 36t sine of t. How would you tackle this piece of the integral? What would be your strategy there? Yeah, it'd be parts. You could use the tabular method on this. That would be parts. Here looks like you're going to be getting minus 12 cosine squared. What would you have to use for that one? Yeah, that'd be your reduction formula there. Your identity, and then this one is just a straight up that's a straight up standard calc integral. So you go through all that stuff. Excuse me. You should get negative 42 pi plus 16. So I'll leave those details to you. All right, so if you got your field F and it's at Mn, then this is your two-dimensional work, circulation integrals, mdy plus mdx plus ndy, right? So you can loosely think of this as think of mdy plus I got it backwards. mdx plus ndy. You can loosely think of this as your mn dot dx dy. So change in x, change in y. So you're looking at x component in the x direction, y component in the y direction. How much of that do we get? that's your work circulation. If we were looking at the looking for flux, looking for that normal component, then you got your F would be Mn. And if you wanted the normal component, then you would have your dy comma minus dx. You just reverse it, make it negative. And if you did that dot product, that would get you down to here. So that first integral we did, if we look at this first integral here, you can interpret this a couple different ways. If we look at x dy minus y dx, if I want to think of this as a work or a circulation integral, I would write it with the dx first. So I'd have a minus y dx plus x dy. And so I'd be looking at the work or circulation of the field minus yx. So that's if I wanted to think about this integral as a work integral. This would be the work or circulation of this field along that parabolic arc. Right. Or I could rewrite it this way. I could keep it as is, x dy minus y dx. I guess I should be a little more specific here. So this would be my m dy or m dx plus n dy. If I kept it this way, I could think of this as the m dy minus n dx. So I could think of this as a flux. So going across of the field f of xy equals xy across C. That'd be your m dy minus n dx. So you notice here these fields, right? Look at the relationship between these fields. These fields are orthogonal, right? I'll call that F2. I'll call that F1. These are orthogonal fields. So it's literally work, circulation, flux. They're literally 90-degree ideas. And we'll talk more about these specific types of integrals next week when we get to Green's theorem. We'll be able to do like this problem we did today. The problem here we did today that took us 3 line integrals to do. Green's theorem next week will let us turn it into 1 double integral. So stay tuned for that. That's the big theorem. Well, we got 2 big theorems coming up next week, actually. Well, one of them we'll get into tomorrow. Okay.